Before we start, we need to really understand what is normal with a machine. And the type of thing that we're talking about is which peaks would you expect to see in the spectral data? What shape should the orbit be? What is the normal running position of the shaft? And what are the normal process conditions? So the first thing you should really try and do is gather information about what's going on. So what's the reported issue? Why have you been asked to go and look at this machine? What has changed? Has there been any recent maintenance? Has the process conditions changed? Are we running at a different load or a different flow rate, for example? It's worth finding out what instrumentation is available and what's fitted on the machine, and is it working? What data is available? Is the signal valid? Could it be a false indication? Many vibration faults turn out not to be a vibration fault initially at all. A lot of them are instrument issues. If it looks real, is there a step change, or is the whatever causes the issue, is it a gradual change? We should always consider that response is equal to force over restraint. So if the restraint goes down, the response goes up. Equally, if the force goes up, the response goes up. So what we'll do first is we're going to take a look at how the typical normal signatures of different types of machines. So to start with, if we just consider a single shaft machine, maybe a compressor or a generator, single shaft with proximity probes, typically there would be fitted 2 probes at each end, 90 degrees apart. And this is the type, if you looked at the data, this is kind of thing what you'd expect to see. In the frequency spectrum, it would be dominated by the 1x response. There may sometimes be a secondary peak there. If you looked at the full spectrum, it should actually be traveling in a forward precession, so this will be dominant. And the orbit we would expect to see typically travel forward precession and maybe slightly elliptical, just because of the different stiffnesses in there. If we looked at the shaft center line, when the machine starts up, if the machine had got plain bearings, you would expect it to actually travel up the bearing housing in the direction of rotation. Whereas if you've got tilting pad bearings that equalize the pressure, you would expect the shaft to kind of move up in a vertical movement. So that's probably normal behavior for a single shaft machine. Now let's take a look at a different type of machine. So in this instance, we're going to talk about a multi-shaft machine, maybe a gas generator with accelerometers fitted to the casings. Now, in this example, the machine has actually got 2 shafts, a high pressure and a low intermediate pressure shaft. And we can see because of that, there's effectively 2 1x signals and 2 2x signals. And if we just look at the red for now, the HP signal, we can see if we plotted this against HP speed, you'll see a linear relationship as the speed increases. So there's your 1x and here's your 2x. And if we also said, hang on, we've got another peak here. This is the radial drive shaft in this instance, and this happens to run at 2.56 times the actual rotational speed of the HP shaft. So if we added that onto the plot, we would see 2.56 run up here. Now, in this machine, there's an eyepiece ball as well, so we're going to expect to see these blue lines going on here, but they're not physically connected. So as this speed increases, it won't necessarily be a linear response from the IP. So you may end up with something that looks a bit more like this, where the speed actually increases, but maybe it doesn't carry on to increase. The actual looking in the time domain, you'd expect, because there's so many actual normal peaks there, that the signature would be quite busy and quite complex. When we looked at a higher frequency in the acceleration domain, you'll see the same peaks low down, what we see here, but then you'll also see maybe some blade passing frequencies. So this will be the number of the blades time on each stage times the actual rotational speed. Okay, so let's take a look at a gearbox, for example. The big difference here is we've got 2 shafts in the gearbox. We've got a low speed shaft and a high speed shaft. Again, we have a dominant 1x peak from both shafts present, maybe 2x as well. But in this instance, they are actually mechanically driven. So a doubling in the high-speed shaft will actually result in a doubling in of the low-speed shaft speed as well. So they track each other. Again, as we saw before, as there's multiple peaks in there, the time waveform will actually look quite complex. We could look down at the low frequency content in the acceleration profile will be here, but instead of blade passing frequency, we're going to have what's known as gear mesh frequencies. So this will be the number of the teeth times the actual rotational speed. And often there's be harmonics of that, either 2 and maybe higher, there would be 3 times that. So that gives you an indication of what a normal machine looks like. So what are the first things that can go wrong? Well, let's have a look. So sometimes actually false indications occur due to glitches run out, and we can also compensate for that, which I'll try and illustrate on this quick bit. So if you imagine this using the same concept here, we're actually running with the machine at a high speed, and as we reduce the speed, we'd expect the frequency to come down like this, and we would expect the actual amplitude of the vibration to drop. But maybe as you reduce the speed, the vibration kind of plateaus and doesn't decrease as expected. And then you get down into what we refer to as slow roll condition. This is where the machine is running significantly or very slow to the extent that it's not physically possible to move the amount of that it's actually the instrumentation is telling you it is. So here you can see this is a much higher. If this thing is only just turning over, how can we have so much displacement? Well, typically it's more likely to be due to something like electrical renewal and variation in shaft conductivity, maybe local magnetic forces, welding operations. Mechanical runout may look like this as well, as would out of roundness and surface imperfections as a few. There are many others. Typically, because it's actually a 1x response, your response would still be mainly a sine wave. Now, another form of a glitch is sometimes if you may actually have a scratch on the shaft. Now, in this instance, we can see on the time wave that for every revolution, there is a mark. And this is where the actual scratch, the displacement probe actually sees this as a movement. Because it's a complex waveform, we end up with harmonics coming in. But we do have the same response where we have a high response at low speed that isn't real. So what can we do about this? Well, we can correct sometimes, with some analyzers allow you to correct for things like this. I'm going to try and illustrate this. Sometimes it's more successful than others, but let's have a go. So if we take this uncompensated data from a pair of proximity probes, and you can see we've got a very messy orbit. This is an unfiltered orbit. So the actual shape of it isn't so bad, but what is happening is there's lots of things going on here. And you can see we've got a high 1x response and a 2x response as well. Now, this is running at 3000 RPM. So if we actually decrease the speed of the machine and look at what it looks like in the slow roll speed, we can see we've still got a significant amount of vibration that's attributable to the 2x. And you can see here that the 2x actually is the second peak here. So what we can do is we can actually take a recording of this and actually remove this content from the signal. And then when we do this, if we run the machine back up to its operating speed, what you'll see is that the signal is a lot cleaner. In this instance, you can still see that it's quite distorted. There's still a lot going on. It's a noisy signal. But what you can clearly see is that the 2x response has been significantly reduced. Let's say compensation is a best practice and should be used where possible. So we're now going to talk about a few different common fault conditions, and we're not going to go into the detail of what the fault condition is. We're going to more talk about how we actually identify it. So to start with, we'll just talk a little bit about imbalance. So if we talk about a static imbalance, then this would predominantly be dominated by a 1x response. You would expect to see this on in the radial direction. And if you looked across the actual probes on the drive end compared to the non-drive end, you would expect them to pretty much be in phase. And between the X and the Y probe on each end, you would expect typically a 90-degree difference. Another type of imbalance is dynamic imbalance. So this changes with the speed. And here you can see the main difference here, we still have a 1x response, but when we look across the machine, you can see that we've got a varying or a phase change across the machine from the drive end to the non-drive end. In this instance, the X and the Y probes themselves would still be pretty much show a phase difference of 90 degrees between each one. In practice, you don't really have static balance and dynamic balance on its own. We're more likely to have a combination of the two, which is basically known as a couple imbalance. Again, imbalance is probably one of the most common reasons for 1x present, but it isn't the only one, and we should always be mindful of that before we try and balance a machine. There could be other things. But with regard to actual imbalance itself, then these are it's a short list of some things that could actually be the cause. So we're talking about damage and material loss, missing or lost balance weights, maybe contamination on the rotating components. This is quite common on compressors that have dirty process gas going through them, for example. Manufacturing or machining errors, assembly errors. In a generator, you may have an uneven mass in the electrical windings, or you could have an eccentric rotor. And rotor bow that's caused by a thermal expansion could also be a cause for imbalance. In this instance, you would expect as the rotor warmed up and the heat normalized, then the rotor would straighten and your imbalance would disappear. So just a few other common fault signatures, just to give you an indication or a taster. We talk about alignment being quite common. So if we were able to look at the axial vibration when we had an angular misalignment between two coupled machines, we would see quite a dominant 1x response, but we'd also see quite strong 2x and 3x being present with 180 degrees phase difference across the coupling in an axial direction. If we had a parallel misalignment where you can see the actual flanges based offset, you would see quite a common thing here would be a very dominant 2x response and maybe smaller radial 1x in both in the horizontal and vertical directions. Again, we would see 180 degrees across the couple in the radial direction in this case. Another common fault condition is rotating looseness, often caused by excessive bearing clearances. In this instance, you would expect to see a strong 1x response with multiple harmonics. The structural looseness is also has a very familiar response here. We're seeing a strong 1x here, and you can see straight away this looks very similar to the imbalancing. So this is typically the type of thing that you would need to eliminate before you went ahead and tried to balance a machine, in case it's down to a looseness, not an imbalance. So you would be looking for soft foot and differences between the foot and foundation. And as a note there, so structural looseness will typically increase the 1x vibration component in the direction of the least stiffness. So consider what the actual machine looks like and how it's actually built and made up before making an assessment on that one. We may see journal bearing wear, and in this instance, we'll potentially see 1x with harmonics, but you'll also potentially see harmonics around the 1x and the 2x, probably decreasing inside as we increase in frequency. If we consider rubs on a machine, this is where we can have a continuous rub or momentary rubs. So again, what we'll look at here is, and sometimes you can have a rub where it actually touches on alternate revolution, so it generates a half X response, and you'll see it's actually a subsynchronous peak is present. Again, you'll get harmonics of those, and it may actually happen that it doesn't rub throughout the speed range. Again, if we plot speed here, we can see the actual half X response comes in just for a portion of the running speed, again with its harmonics here and here. So no rub, rub, and clear again. And if we looked at the orbit, you would see in this instance, you can see 2 cycles of rotation. There's the first one, and the second one for 1 cycle of vibration, which is giving you your half X response. If we consider looking at orbit plots, some of the other things that we can actually use it to understand is the actual amount of preload on the machine. So in a perfect world with fully equal forces, we would expect an orbit to be almost perfectly round. In practice, that never really happens. You'll always have a certain degree of preload, and that's basically because the actual stiffness in one direction is never really going to be totally equal to the other. So this is quite a normal illustration of an orbit. However, if there's some force put up on the rotor to push it over, then you may sort of start to see this squashing of the profile. And if we increase the actual force in this direction even further, then we can actually get a very heavy preload, which actually results in the almost reverse precession of the thing going around there. When you've got heavy preloads, you can also look at the shaft center line and consider it to what it would be like normal. If this was a tilting pad machine, you would expect that when the rotor started up, it would just move vertically like this. However, in this instance, maybe it's got being pushed over. There's either an alignment or some preload holding it over to one side. Now, typical reasons for things like this to happen could be a coupling misalignment, maybe a locked coupling, or maybe your thermal or external forces. We can even get gravitational preloads, bearing preloads, and even fluid preloads. So I'm now going to just tell you a little bit about another fault condition, just to wrap up. So I'm going to tell you a little bit about oil whip and whirl. So what happens when we start to, on a typical bearing housing, we'll have an oil wedge supporting the actual rotor. But what can happen is that the oil starts to become unstable and starts to actually rotate around the bore. When this happens, this is what's known as oil whirl. So, how do we see this? Well, if you imagine the oil on the stationary component is going to be static, and the oil on the rotating component is going to be running at rotational speed. So on average, it's kind of about 50%. And when you take in the potential losses, you would expect to see a response that's actually subsynchronous below 50%, typically between 35 and 49% of the rotor speed in a sleeve bearing. So this can be a problem, but it only becomes a real problem when the actual frequency of the oil whirl starts to actually get close to the actual natural frequency of the rotor's first critical. In this instance, when the rotor increases matches on there, the actual peak can lock onto the excitation can lock onto the first critical and excite it, and basically result in a very destructive situation. So just as a final thing, to give you an illustration on what this would look like if you're looking at the data, you would, as we mentioned, you would potentially have this quite dominant subsynchronous peak, typically between 0.38 and 0.48x compared to your normal 1x frequency. If you looked at your an orbit plot, you would see two rotations of the machine for 1 cycle of vibration, and it's going in backwards because it's actually growing slower, it's slightly slowing down. And then if we plotted it and looked at, as we saw this, as we increase, you'll see that this is actually getting slightly slower, but then something happens. So the first thing we need to understand is what this grey line means. So this is the first critical mode. So if you look at the actual amplitude of the vibration here, you'll see as we go, as the 2x forcing corresponds with the first critical mode, there's a bit of a peak, and then it drops away again. And then as the first critical crosses over the the 1x crosses over the first mode, we end up with the first critical point here, and you can see this peak. Now, as we increase, what can happen is that the forcing frequency from the oil well actually corresponds with the frequency of the mode. Now, in this instance, it won't continue up. It'll potentially lock on. So as you increase in speed, the actual frequency of the oil will not increase, it locks on. But what will happen is your actual levels of vibration will basically increase to a very destructive level. This is potentially very dangerous for a machine unless it's actually brought back under control very quickly. If you could see the orbit, you would see as the speeds increase, but the actual frequency hasn't, we've actually got more cycles, rotating cycles, for one cycle of vibration. And again there. So this was just intended to give you a little bit of insight in some of fault conditions and what they may or may not look like. It's not a definitive guide, and there are many exceptions to the rules, but I hope that's useful. My name is Rick O'Connor, and thank you very much for your time.